morning to one and all. I am Venkadesham. I am going to discuss about photoelectric effect. In this video, I am going to explain the photoelectric effect topic, and which is one of the important topic in the atomic structure. This photoelectric effect is actually, it was introduced by the scientist called as there is an Hedge is a scientist. He's carried out so many experiments in the lab, and he has observed that when a beam of light striking on the metal surface, and there is an ejection of electrons takes place from the metal surface, and that phenomenon is it's a photoelectric effect. Whatever the electrons ejected from the metal surface, these electrons are called as it's a photoelectrons. It's a photoelectrons, and this light definitely with the suitable frequency, there is a ejection of electrons can be takes place. At that frequency is called as it's a threshold frequency, and the light which is having the minimum wavelength to eject the electron from the metal surface, that wavelength is called as it's a threshold wavelength. Frequency which is less than the threshold frequency striking on the metal surface, there is no question about ejection of electron from the metal surface. That the time there is no question about that photoelectric effect. That means to occur the ejection of electron and a light of frequency which is greater than or equals to its threshold frequency, then only there is a ejection of electron from the metal surface can be takes place. And when a beam of light is striking on the metal surface, there is a ejection of electrons takes place from the metal surface, and that phenomenon is a photoelectric effect, and the electrons is called as it's a photoelectrons, right? Light of a minimum frequency for the ejection of electrons is there. That frequency is called as it's a threshold frequency, and a light of suitable wavelength should be required to eject the electron. That wavelength is it's a threshold wavelength, right? So if the light with lesser frequency than the threshold frequency, there is no ejection of electrons is observed. If the light with more than or equals to there is a threshold frequency, then there is a photoelectric effect is observed, or ejection of electrons from the metal surface is observed, right? And here we can observe that there is a Hedge is given the another important point. There is no time gap between the ejection of electrons. When the light of suitable frequency is striking on the metal surface, there is no time gap between the striking on the metal surface and immediately there is an ejection of electrons can be takes place, right? And here number of electrons ejected from the metal surface is directly depends upon the its intensity of light or brightness of the light, and it is independent of its frequency of the light, whereas excess amount of frequency which is applied more than this threshold frequency, and that frequency can be converted in the form of its kinetic energy for the photoelectrons. This kinetic energy is which is depends upon the its frequency of light, and it is independent of its intensity of light, right? And here number of electrons ejected from the metal surface is purely depends upon the intensity of the light, whereas the kinetic energy is ejected photoelectrons is definitely associated with some amount of energy, that is a kinetic energy. This kinetic energy is directly proportional to the its frequency of the light, and it is independent of its intensity of the light. Later there is Einstein is a scientist. He has explained Einstein is a scientist. He has explained this photoelectric effect in terms of energy criteria. Einstein explained the photoelectric effect based on the Planck's quantum theory, and according to him there is a metal is in which there is electrons are held together with strong attractive forces, and whenever the beam of light which is striking on the metal surface, this beam of light, definitely some minimum amount of energy should be possessed. This minimum amount of energy which is required to eject the electron is it's a work function, or it is also called as a photoelectric work function, or generally it can be represented by a symbol W naught. According to the Planck's theory, the energy is directly proportional to the it's a frequency, so that I can write here work function W naught is equals to h nu naught. Whenever the excess amount of energy of a light which is striking on the metal surface, the excess amount of energy will be transferred to the photoelectrons in the form of kinetic energy. So that's the reason, and we can tell that here kinetic energy is which is purely depends upon the its frequency of light, and it is independent of intensity or the brightness of the light, right? And that's the reason we can write here kinetic energy Ke is always we will write down this is a work function W minus this is in a work function W naught, and kinetic energy I can write down mv square that is equals to here h nu minus h nu naught. You can remove the proportionality here, or you can write hc by lambda minus this is an hc by here it is a lambda naught. Okay, so here half mv square is equals to hc, you can take comma here lambda naught minus lambda divided by here it is a lambda and a lambda naught. So this is a final equation we'll write down for the it's a kinetic energy. Okay, generally if you plot a graph between the it's a kinetic energy versus and a frequency, and kinetic energy versus its intensity, and generally kinetic energy of the photoelectrons is directly depends upon the its frequency, so that your kinetic energy if you are taking on the y-axis and its frequency is taking on the x-axis, and you will get a one straight line, and here this frequency is it's a threshold frequency nu naught, and you will get a straight line like this. This shows that kinetic energy is directly proportional to the depends on the its frequency. And if you plot a graph between the kinetic energy and its intensity, and you will get a one straight line which is it's a kinetic energy equals to which is a constant. Kinetic energy is equals to constant. You will get a straight line which is parallel to the this intensity axis one. The number of photoelectrons ejected is directly proportional or directly depends upon the its intensity of the light, the brightness of the light, and it is an independent of its frequency. When we are talking about this particular work function, our work function is which is a characteristic for the given metal, and it is purely depends upon the ionization energy, and whenever there is a more ionization energy is there, definitely its work functions also are going to be the more. If it is a more ionization energy is there, more is a work function, and if it is metal is having the low ionization energy, then it is having the low work function, and these work function values are purely depends upon the nature of the metal. Here stopping potential is another word is there. This stopping potential is the potential which is required to stop the ejection of electrons. The potential which is required to stop the ejection of electrons is it's a stopping potential, and stopping potential I can write down generally as a V naught is it can be represented by a symbol V naught. V naught is it's a stopping potential. Stopping potential, the potential which is required to stop the ejection of electrons from the metal surface is it's a stopping potential, and it is represented by a symbol V naught, and this kinetic energy of the photoelectrons is always which will be equals to the it's a EV naught, or I can write this is a kinetic energy of mv square is equals to which is EV naught. If V naught is it's a stopping potential. Einstein is given that there is a mass and a energy relation, and there is an energy of the photon and mass of the electron relation is given by the Einstein, and we can write down E equals to, which is in mc square, which is an Einstein equation, Einstein mass and the energy relation. We can say m is the mass of photon, and c is the velocity of photon is c.